An estimate is a number you compute from data to approximate an unknown truth about a population or process. The unknown truth is often called a parameter, which could be a population mean, a population proportion, a rate per person time, a difference between groups, or an association measure like a risk ratio. The estimate is your best guess based on the information you observed. It is not guaranteed to equal the truth, because your sample is only one slice of the broader reality. This is why estimates come with uncertainty. For example, a sample proportion of 0.25 is an estimate of the true underlying probability of the event in the target population over a defined window. Another example is a sample mean cost of $1,200, which estimates the true average cost in the population you are studying. A third example is a rate of 3 events per 100 person years, which estimates the underlying event frequency scaled to time at risk. What an estimate represents depends on the unit of analysis and the definition of the denominator. This is a key reason estimates can be technically correct, but conceptually mismatched. If your unit is people, your estimate represents an average or probability per person. If your unit is visits, your estimate represents an average or probability per visit. If your unit is person time, your estimate represents an event rate per unit time. These estimates answer different questions because they describe different sample spaces. For example, probability of receiving a service per visit can be low even when probability a person receives the service at least once per year is high, because frequent visitors have multiple opportunities. Fusu. Another example is that mean cost per claim line differs from mean cost per person, and these can tell different stories about burden. A third example is that incidence per shift differs from incidence per hour, and the right choice depends on whether you want to compare across shifts of different length. Defining what the estimate is per and among is part of defining what the estimate represents. Estimates also represent a specific time and context. A population parameter is not always a timeless constant. It can shift as the population changes, policies change, measurement changes, or the data capture system changes. This means your estimate is always an estimate of the parameter in a defined context, not an eternal property. For example, an estimated prevalence in 1 year represents prevalence in that year under that year's measurement practices. Another example is an estimated program completion rate in a quarter, which represents performance under that quarter's operational context and participant mix. A third example is an estimated diagnostic test positivity rate in a season, which reflects both disease prevalence and testing strategy during that season. Recognizing the time and context makes estimates more interpretable and prevents overgeneralization. A useful way to view an estimate is as a function of the sample. You apply a rule to the data, and the rule outputs a number. Different rules can estimate the same underlying parameter, and some rules have better properties than others. For example, the sample mean is a common rule for estimating the population mean, but for skewed data, the median can be a better estimator of typical value depending on what typical means for the decision. Another example is that you can estimate a proportion using the raw fraction, but you can also apply smoothing or model-based approaches when data are sparse. A third example is rate estimation, where the basic rule is events divided by person time, but in small area settings, you might use methods that stabilize rates to reduce noise. These choices are not just technical, they define what you mean by the estimate and what behavior you want under repeated sampling. Estimates also carry implicit assumptions about what the observed data are and how they relate to the target population. If data are a random sample from a well-defined target, an estimate can be interpreted as an unbiased approximation to a population parameter with quantifiable sampling variability. If data are not a random sample, the estimate may still be useful as a description of the observed sample, but it may not represent the broader target population accurately. For example, an estimate from a convenience sample can describe that sample precisely but may not generalize. Another example is an estimate from service user data, which describes those who used services rather than all who might need them. A third example is an estimate from a survey with differential non-response, which may need weighting to better represent the population. Being explicit about whether you are estimating a sample description or a population quantity is part of stating what an estimate represents. Finally, an estimate becomes most meaningful when it is framed in practical terms. A number by itself is rarely the full message. You want to connect it to a clear definition and to the real-world meaning of the numerator and denominator. For example, instead of saying the estimate is 0.112, you would frame it as about 12 out of 100 eligible individuals experienced the event during the defined period. Instead of saying the mean difference is 5, you would frame it as Group A averaged about 5 units higher than Group B on the measured outcome, while still being clear about the scale. Instead of saying the rate is 0.03, you would frame it as about 3 events per 100 person years. This framing is not cosmetic. It is what makes the estimate interpretable and transferable across different job settings. A confidence interval is a range of plausible values for an unknown parameter built from your data using a defined method. The most common confidence level is 95%, but the key is that the confidence level refers to the procedure, not to a single interval after it has been computed. The practical meaning is this: if you repeated the same sampling process many times and built a 95% confidence interval each time, about 95% of those intervals would contain the true parameter. In a single analysis, your interval either contains the true value or it does not, but you do not know which. The confidence level describes how reliable the method is over repeated sampling. For example, if you compute a 95% confidence interval for a population mean, the interval is a data-based range generated by a procedure designed to include the true mean most of the time under repeated sampling. Another example is a 95% confidence interval for a proportion, which is built to capture the true underlying probability with a specified long-run frequency. A third example is a 95% confidence interval for a rate per person time, which is built to capture the true underlying event rate given the observed event count and exposure. A very common misunderstanding is to treat a 95% confidence interval as a probability statement about the parameter in the specific dataset, such as there is a 95% chance the true value is in this interval. That is not the standard frequentist interpretation. The parameter is treated as fixed, and the interval is random because it depends on the sample. The correct statement is that the method used to construct the interval has 95% coverage under repeated sampling, assuming the model and sampling assumptions are appropriate. In practice, you can still communicate the interval as a range of plausible values supported by the data, but you should avoid framing it as a probability that the parameter lies inside the interval in this one case. For example, it is appropriate to say values in this range are consistent with the data under the model assumptions. Another example is to say the interval reflects uncertainty from sampling variation. A third example is to say the estimate is X and the confidence interval shows the range of values we would not be surprised to see for the true parameter given this data. Confidence intervals also do not mean that 95% of individual outcomes fall in the interval. The interval is about a population parameter, not about the distribution of individuals. This is a frequent confusion when people see a confidence interval around a mean and assume it describes the spread of data. For example, if you report a mean value with a 95% confidence interval, that interval is about uncertainty in the mean, not about where 95% of individuals fall. The spread of individuals is described by percentiles, standard deviation, interquartile range, or prediction intervals, depending on the context. Another example is a confidence interval around a proportion. It is about uncertainty in the underlying probability, not about variability in individual binary outcomes. A third example is a confidence interval around a regression coefficient. It is about uncertainty in the parameter, not about uncertainty for any individual prediction. Keeping this distinction clear prevents you from using the wrong interval for the wrong communication goal. Confidence intervals are most useful when you interpret them as supporting a range of practical effects, rather than as a binary significance device. A narrow interval means high precision and suggests that the parameter is well pinned down by the data. A wide interval means low precision and suggests that many values are plausible given the data. The key is to look at the entire range and ask what it implies for real-world decisions. For example, if a risk difference confidence interval ranges from a small negative value to a small positive value, it suggests that the data are consistent with little to no difference and that any difference is likely small in magnitude. Another example is a rate ratio interval that ranges from near 1.0 to noticeably above 1.0, suggesting the data are consistent with no difference up to a moderate increase, which may require more data or better design to clarify. A third example is an interval for a mean difference that is entirely above 0, but still small, suggesting a real difference that might or might not be practically meaningful. Confidence intervals are therefore a bridge between statistical uncertainty and practical interpretation. IT is also important to understand what a confidence interval assumes. Most intervals rely on a model or approximation, such as a normal approximation for the sampling distribution, a count-based model for rates, or a regression model for adjusted comparisons. If those assumptions are violated, the interval can be too narrow or too wide, meaning its coverage can be wrong. For example, a normal approximation confidence interval for a proportion can behave poorly for rare events or small samples, sometimes producing bounds below 0 or above 1. Another example is a confidence interval for a mean computed under an independence assumption that is violated by clustering, which can be too narrow because correlation reduces effective sample size. A third example is an interval around an adjusted estimate from a model that is misspecified, where the uncertainty may not reflect real-world variability. This is why earlier topics like distribution shape, design-based variability, and model assumptions matter for confidence intervals. Finally, confidence interval interpretation becomes clearer when you pair intervals with clear parameter definitions and units. An interval without context can be hard to interpret. You want to specify what the parameter is, what population it refers to, and what time period it covers. For example, a confidence interval for a risk should specify the time window, such as 30-day risk or 1-year risk, because risk depends on time. A confidence interval for a rate should specify the rate scale, such as per 100 person years, because the numeric value changes with the scaling. A confidence interval for a difference should specify which groups are being compared and how the groups are defined. When the parameter is clear, the confidence interval becomes a powerful summary. It tells you what value you estimate, how uncertain that estimate is, and what range of effects are consistent with the data under the chosen method. Confidence interval width is a practical summary of precision. A narrow confidence interval means your estimate is relatively precise, and a wide interval means your estimate is relatively uncertain. The main reason confidence intervals differ in width is that they reflect standard error, which is the expected variability of the estimate across repeated samples under the same process. When standard error is larger, the interval widens. When standard error is smaller, the interval narrows. This is why confidence interval width is not a cosmetic feature of reporting. It is a direct indicator of how stable an estimate is likely to be and how much room there is for alternative plausible values. For example, a subgroup estimate based on a small denominator will usually have a wider interval than a statewide estimate based on a large denominator. Another example is a rare event rate with few events, which will have a wide interval even if the person-time denominator is large. A third example is an adjusted estimate from a model with many parameters relative to the sample size, which often yields wider intervals because more uncertainty is introduced by estimating more components. Sample size is one of the strongest drivers of interval width because more information typically reduces standard error. As sample size increases, the standard error of many estimates decreases roughly with the square root of sample size, which means interval width shrinks, but with diminishing returns. This has practical implications. Doubling the sample size does not cut the interval width in half. It reduces it by about a factor of square root of 2. For example, moving from 100 to 400 observations tends to reduce standard error by about half, which narrows the interval substantially. So there's another example is that small sample size differences can matter a lot when the outcome is rare, because adding a few events can change the stability dramatically. A third example is that in time series monitoring, aggregating from monthly to quarterly can increase the effective sample size per time point and narrow intervals at the cost of less time resolution. Sample size is therefore both a design consideration and a reporting interpretation tool. Outcome variability is another major driver of confidence interval width. For continuous outcomes, more spread in individual values increases the standard error of the mean and therefore widens the interval around the mean. For binary outcomes, the standard error depends on the underlying proportion and tends to be largest when the proportion is near 0.5 and smaller near 0 or 1 for a fixed sample size. For count-based rates, fewer events lead to higher relative uncertainty, which widens the interval, especially when event counts are low. Examples include cost data being highly variable, which makes mean cost intervals wider than mean age intervals at the same sample size. Another example is that a proportion of 50% is typically less precise than a proportion of 5% at the same denominator, because balanced outcomes produce more sampling variability. A third example is a rate based on 2 events versus 20 events, where the 2-event rate will have much wider uncertainty relative to its estimate. Variability is therefore not just about sample size. It is also about the nature of the outcome. Design effects are a key driver of interval width in real-world data because they change the effective sample size. Clustering increases interval width because correlated observations provide less independent information than the raw count suggests. Weighting can increase interval width when weights vary widely because a small number of heavily weighted observations can dominate the estimate. These design-based features widen confidence intervals compared with what you would expect under simple random sampling. For example, 2 data sets with the same number of individuals can have different interval widths if one is spread across many clusters and the other is concentrated in a few clusters. Another example is a weighted survey estimate where the weighted effective sample size is much smaller than the raw respondent count, resulting in wider confidence intervals. A third example is repeated measures data, where treating repeated rows as independent would artificially narrow intervals. Properly accounting for correlation widens them to a more honest level. Design effects are often invisible unless you intentionally check for them, which is why they are a recurring theme in applied biostatistics. The chosen confidence level also affects interval width, because higher confidence requires a wider range to capture the true value more often. A 99% confidence interval will be wider than a 95% interval, and a 90% interval will be narrower than a 95% interval, all else equal. This is a direct trade-off between certainty and precision. Higher confidence means more conservative coverage, which requires wider bounds. Examples include a report that uses 95% intervals for standard reporting, but uses 90% intervals for exploratory internal monitoring, where the goal is to detect potential changes early. Another example is a high-stakes setting where 99% intervals are used to reduce the chance of missing true uncertainty. A third example is comparing 2 studies where one reports 90% intervals and the other reports 95% intervals. The width difference partly reflects the chosen confidence level, not just data quality. The confidence level is a reporting choice that should be consistent within a product to avoid confusing readers. Finally, the method used to construct the interval can change width because different methods make different approximations, especially in small samples, rare events, skewed data, and bounded outcomes. Some methods produce symmetric intervals while others produce asymmetric intervals that better reflect the underlying distribution. For example, a normal approximation interval for a proportion can be too narrow or produce impossible bounds when events are rare, while alternative proportion intervals can be more accurate and may appear wider or more asymmetric. Another example is mean confidence intervals under heavy skewness, where bootstrap intervals may better reflect uncertainty and skewness than normal-based intervals. A third example is rate intervals, where count-based methods can yield asymmetric bounds that reflect the discrete nature of events. Interval width is therefore not only about the data, it is also about whether the interval method matches the data structure. The most practical way to interpret confidence interval width is to treat it as a signal about decision readiness. If an interval is narrow enough that all values in the range would lead to the same decision, the estimate is often actionable, even if it is not perfect. If an interval spans values that imply very different decisions, the estimate may not yet be reliable enough for strong conclusions, and you may need more data, better measurement, a different design, or a different estimation strategy. For example, if a program effect interval includes both meaningful improvement and no improvement, it suggests uncertainty that may require additional follow-up. Another example is a subgroup rate interval that is so wide that ranking subgroups is not stable, suggesting you should avoid strong comparisons. A third example is a time trend interval that is wide month to month, suggesting you should aggregate over longer periods for more stable monitoring. Confidence interval width becomes a practical tool when you interpret it as how much uncertainty remains, not just as a technical output. The bootstrap is a resampling approach for estimating uncertainty when standard formulas are hard to trust or hard to derive. The basic idea is to use your observed dataset as a stand-in for the population, then repeatedly resample from it to mimic repeated sampling. Each resample is called a bootstrap sample. You compute the statistic of interest on each bootstrap sample, and then you study the distribution of those bootstrap statistics. That distribution acts like an estimated sampling distribution, which gives you an estimated standard error and a way to build confidence intervals. This is especially helpful when the statistic is complicated, the data are skewed, the sample is small, or the estimator has a non-normal sampling distribution. For example, a median often has a sampling distribution that is not well captured by simple formulas in small samples, and Bootstrap can estimate its uncertainty. Another example is an estimator based on ratios, like rates or percent change, where analytic standard errors can be messy. A third example is an adjusted estimate from a complex pipeline, where you want uncertainty that reflects the whole process rather than a simplified formula. Bootstrap intuition works best when you treat it as a simulation of repeated sampling that is driven by the data you have. You are not creating new information. You are using resampling to approximate how your estimate would behave if you could repeat the sampling process. The key is that Bootstrap variability reflects what is in your sample. If your sample does not contain certain patterns, the Bootstrap cannot invent them. For example, if your sample has very few extreme values, the Bootstrap distribution may understate tail uncertainty because it keeps reusing the same observed values. Another example is if your sample is biased, the Bootstrap will give precise uncertainty around the biased estimate because it resamples from the biased sample. A third example is if your sample is very small, Bootstrap resamples may repeat observations many times, and the Bootstrap distribution may be rough or unstable. The Bootstrap is therefore a tool for uncertainty estimation, under the assumption that the sample is a reasonable proxy for the population or process. Bootstrap becomes particularly valuable in non-standard settings, meaning situations where typical confidence interval formulas can be misleading. One common non-standard setting is heavy skewness, where normal-based intervals for the mean or for differences can perform poorly at modest sample sizes. Another is bounded outcomes, like proportions near 0 or 1, where symmetric normal-based intervals can produce impossible bounds or poor coverage. Another is robust statistics, like medians, trimmed means, and quantiles, where the sampling distribution is not naturally symmetric or where variance formulas are less familiar. Examples include estimating uncertainty for median cost, uncertainty for a 90th percentile wait time, and uncertainty for a ratio measure like cost per completed case. In these settings, Bootstrap often produces intervals that better reflect asymmetry and real data shape. Another non-standard setting is when your estimate is produced by a multi-step pipeline and you want uncertainty that reflects the whole pipeline rather than just one component. For example, you may clean data, recode variables, apply inclusion criteria, aggregate to person level, and then compute a rate. A formula-based standard error may reflect only the final step and ignore the impact of upstream decisions and variability. Bootstrap can be applied to the workflow by resampling at the appropriate unit, rerunning the pipeline on each resample, and then summarizing the variability of the final statistic. Another example is a model-based estimate combined with a derived transformation, such as a predicted probability difference derived from a fitted model. A third example is a complex composite measure that sums or weights multiple components. The Bootstrap's strength is that it can capture uncertainty of the entire procedure as a black box, as long as resampling is done correctly. Resampling must respect the data structure, and this is where Bootstrap can go wrong if applied mechanically. If your data are clustered, you often need cluster bootstrap, meaning you resample clusters rather than individual rows so that within cluster correlation is preserved. If your data include repeated measures per person, you often need to resample at the person level rather than at the row level, so the repeated measures structure remains intact. If your data come from a complex survey with weights and clustering, the Bootstrap needs to be adapted to the design, or a design-based replication method may be preferred. Examples include resampling clinics rather than patients when the clinic is the unit that drives correlation, resampling individuals rather than visits when visits are nested within individuals, and avoiding naive row-level resampling when your dataset includes multiple correlated records per entity. The principle is that the Bootstrap should mimic the original sampling design as closely as possible. Bootstrap confidence intervals can be constructed in multiple ways, and the choice affects interpretation. A percentile Bootstrap interval uses the percentiles of the Bootstrap distribution as the interval bounds. This is intuitive and often works well, especially for asymmetric distributions. Another approach uses Bootstrap-based standard errors with a normal-like approximation, which can be less appropriate when the Bootstrap distribution is skewed. There are also bias-corrected approaches that try to adjust for bias in the Bootstrap distribution. The main practical point is that Bootstrap intervals can be asymmetric, and that asymmetry is often a feature, not a problem, because it reflects the data's shape. Examples include a median cost interval that is wider above the estimate than below, or a rate ratio interval that is naturally multiplicative and therefore asymmetric on the original scale. Bootstrap intervals are most informative when you interpret them as reflecting the empirical uncertainty implied by your observed data and method. Finally, the Bootstrap is a learning tool as much as an inference tool because it makes uncertainty visible. When you look at a Bootstrap distribution, you can see whether your estimate is stable, whether it is skewed, and whether it is sensitive to a small subset of influential observations. For example, if the Bootstrap distribution is wide and irregular, it suggests the estimate is unstable and may depend heavily on which observations are included. Another example is a Bootstrap distribution with a long tail, suggesting that the estimate can shift upward substantially in some resamples because of rare extremes. A third example is a Bootstrap distribution that looks multi-peaked, which can happen in small samples, or when the estimator behaves differently depending on which subgroup is represented. These patterns can guide you to use robust summaries, to reconsider modeling choices, or to collect more data. Reporting estimates with practical meaning means translating statistical outputs into statements that clearly describe what was measured, for whom, over what time window, and on what scale. The goal is that a reader can understand the estimate without needing to reverse engineer the numerator and denominator. In applied biostatistics, an estimate is only as useful as its definition. A single number like 0.08 can represent a risk, a rate, an odds, a proportion per visit, or a change score, and those are not interchangeable. Practical reporting begins by stating the unit of analysis and the population being described. For example, You might report a risk among eligible individuals during a 1-year period, a rate per 100 person years among those under observation, or a mean difference in a continuous outcome between two groups. Another example is reporting a percent of encounters with a service, which is distinct from percent of people with at least one service. A third example is reporting an average per facility, which is distinct from an average per person. A practical estimate statement usually includes a numerator, a denominator, and a time window when relevant. This is what makes the estimate portable across settings, because the reader can map it onto their own context. For a proportion, the numerator is the number with the outcome side, and the denominator is the number eligible or observed. For a rate, the numerator is the number of events, and the denominator is the person time or exposure opportunity. For a mean, the numerator is not expressed directly, but you still describe the data that were averaged and the measurement scale. Examples include reporting about 12 out of 100 eligible individuals experienced the event during the year, which makes the denominator explicit. Another example is about 3 events per 100 person years, which makes the time-based denominator explicit. A third example is the average wait time was 18 minutes, which makes the measurement unit explicit. These statements prevent confusion about what percent or rate actually means. Practical meaning also includes choosing a scale that the audience can interpret quickly. Some scales are mathematically convenient but not intuitive. Scaling does not change the underlying information, but it changes how easily the estimate can be understood. For rates, it is often clearer to report per 1,000 or per 100,000 rather than per 1 because the raw per 1 rate can look tiny and hard to compare. For risk differences, reporting in percentage points can be clearer than reporting as a raw proportion difference. For ratio measures, expressing the ratio as X times can be clearer than reporting a log scale or a coefficient. Examples include converting 0.0004 events per person year into 40 events per 100,000 person years for readability, converting a difference of 0.03 into 3 percentage points, and converting a ratio of 1.25 into 25% higher if that framing matches the audience's needs. The key is that the scale should support accurate interpretation without inviting exaggeration. Reporting with practical meaning also means pairing point estimates with uncertainty in a way that supports decisions rather than just technical completeness. Confidence intervals are often the simplest and most interpretable. The practical framing is that the confidence interval shows the range of values that are consistent with the data under the chosen method, which helps the reader judge whether differences are precise and whether they could be practically small or large. Examples include reporting a rate with a confidence interval, showing that the true rate could plausibly be somewhat lower or higher than the point estimate. Another example is reporting a difference with an interval that includes values near 0, which indicates the data do not strongly pin down the direction and magnitude. A third example is reporting a subgroup estimate with a wide interval and noting that the estimate is unstable due to small counts. Uncertainty reporting prevents overconfident decisions based on a single number. A strong, practical reporting habit is to keep comparisons aligned with what you want the reader to conclude. If your goal is to describe burden, you often report counts alongside rates, so readers see both absolute impact and relative frequency. If your goal is to compare groups fairly, you often report adjusted estimates or standardized rates alongside crude values, clearly labeling what adjustment means. If your goal is monitoring over time, you often report a time series of rates with consistent denominators and note any data capture changes that affect comparability. Examples include a table that shows events, population, and rate for each region, so both volume and risk are visible. Another example is reporting crude and age-standardized rates together to separate burden from composition effects. A third example is a trend report that includes both the outcome rate and a data quality indicator, such as percent missing, so changes can be interpreted responsibly. Practical meaning comes from matching the reporting format to the decision need. Finally, Reporting estimates with practical meaning includes writing limitations and definitions as part of the estimate, not as an afterthought. Readers make decisions based on what they think the estimate represents, so you want to state what the estimate does and does not cover. Examples include stating when the estimate applies only to people observed in a system rather than to the full eligible population, stating when the estimate uses visit-level denominators rather than person-level denominators, and stating when the estimate is based on small numbers that reduce stability. Another example is noting when measurement may differ across sites, which affects comparability. A third example is noting when an estimate reflects recorded events and may be affected by documentation practices. These statements do not weaken the estimate. They make it trustworthy and usable because they tell the reader the correct boundaries of interpretation.